Antiderivatives. All right, we're going to learn antiderivatives. We're also going to learn about indefinite integration. Turns out they're the same thing. We'll see. Suppose you were asked to find a function, capital F, common notation, whose derivative is f of x equals 3x squared. From your knowledge of derivatives, you would probably say that capital F of x, the function whose derivative is 3x squared, is x cubed, because if you took the derivative of x cubed, you'd get 3x squared. Right? You follow me? So the function capital F is an antiderivative of f. So antiderivatives are just converses of derivatives. You're going backwards. Okay? So since it's true, yes, it will. It will mess with you. Eventually it won't, but for a while you'll take a derivative when you meant to do an antiderivative and vice versa. Just you will. So if we have capital F of x equals x cubed and little f of x equals 3x squared, isn't it proper to say that little f of x is the derivative of capital F of x? It is also proper to say that capital F of x is not the antiderivative, an antiderivative of little f of x. Now, here's why it's not the antiderivative. If I took the derivative of capital F, wouldn't I still get little f? So see, there's always more than one antiderivative, always, because you can always just add a constant to it. Okay? So, what we're going to have to learn then is the process of going backwards, the process of finding antiderivatives. You know, for one like this one gave us, now that you see how it works, or you see one example, you could probably do others of about this difficulty just by kind of trial and error in your head. But how long do you think that's going to be okay? For like a paragraph in the book, okay? Not a coefficient, a constant. Like that. Plus some constant. Like that. You don't know what it looks like. Because think about it. If capital F of x is x cubed plus 2, is its derivative 3x squared? Yes. So it's an antiderivative of 3x squared. If capital F of x equals x cubed minus 3/4, is its derivative 3x squared? That's just it. There's not one original function. There's a family of those functions that have the derivative of 3x squared. So that's it. So you won't find one antiderivative unless you're given more information about that antiderivative. Okay? All right, note that capital F is called an antiderivative of f rather than the antiderivative of f because of what we just talked about. So capital F could be x cubed, it could be x cubed minus 5, it could be x cubed plus 97. So we just write it as x cubed plus c, where c is some constant. We don't know what that constant is, do we? We have no way of knowing what that constant is. Okay? All right. So our theorem here. If f is an antiderivative, and this gets cumbersome for me too saying this. If capital F is an antiderivative of little f on an interval, then g Capital G is also an antiderivative of little f on that same interval if and only if capital G is of the form capital G of x equals capital F of x plus C for all x in that interval and where C is a constant. Now, that's a very mathy way of saying that any function has more than one antiderivative, and these antiderivatives differ by a constant. Okay? So it's G and F must be identical, except for the constant at the end. All right? So like here, when I called both of these capital F, they're both antiderivatives, aren't they? And they just differ by a constant. That's all they differ by. All right? So that's what that theorem's telling us. Make sense? All right, let's keep going. Using that theorem, you can represent the entire family of antiderivatives of a function by adding a constant to a known antiderivative. So if you can find one antiderivative, all you got to do is say plus C, and that represents all of them. For example, knowing that the derivative of x squared equals 2x, you can represent the family of all antiderivatives of f of x equals 2x by capital G equals x squared plus C. Because x squared is an antiderivative of 2x, so x squared plus C represents the family of antiderivatives of 2x. And C is a constant. Okay? Now, this C is called the constant of integration. The family of functions represented by capital G is the general antiderivative. All right? Because we will get into specific antiderivatives, but only when we're given more information. Okay? We must be given more information to know which specific or particular antiderivative we're talking about. So when you have the plus C written there, you don't know what C is, it's just a plus C. That's the general antiderivative. Now, that general antiderivative can also be called the general solution of the differential equation. Wow, there's a lot of stuff that matters here in this one little slide. The general solution of the differential equation, capital G prime of x equals 2x. Now, a differential equation is an equation with a derivative in it. Okay? Usually, it's in the form of f prime of x equals, can be with the derivative embedded somewhere in the equation. It's usually like this. Now, let's kind of stick with the notation we're used to. We're not used to seeing capital G prime. We're used to seeing f of x equals, in this case, let's call it x squared plus c, and capital and f prime of x. Well, what's the derivative of x squared? 2x. What's the derivative of the constant? 0. So that's more like what we're used to seeing, correct? This can be called a differential equation because it's an equation. How do I know it's an equation? It's got an equals in it with a derivative in it. It's an equation with a derivative. Where's the derivative? Right there, f prime of x. So the antiderivative, I said the, didn't I? An antiderivative, this, is a solution of a differential equation. So the process of finding an antiderivative is the exact same process as finding a solution of a differential equation. Now, we need to be used to both, of thinking of it as both ways, because you'll be asked it both ways. But you got to understand, finding an antiderivative and finding a general solution of a differential equation are the exact same thing. Sometimes it's a little nicer in your head to think of it one way than the other way. You got to get to the point where you understand the process of an antiderivative is the process of a general solution of a differential equation. And that's a whole lot of vocabulary and just, I don't know, it's a lot of words. Plus, all of a sudden, we're going backwards. Okay? So, even though a month from now, you'll look back at this and it'll make complete sense. In fact, you'll wonder why it ever made you pause to think. Right now, it's making you pause to think. A lot of new words, and we're going backwards. Okay? All right. A differential equation in x and y is an equation that involves x, y, and derivatives of y. All right, the way I wrote this one, it involves x, f of x, and derivatives of f of x. All right, you see the x here and here. You see the f of x here. You see the derivative of f of x here. So, again, notation can be a problem, can't it? F prime of x is the same thing as y prime. F of x is the same thing as y. Or we can do what they did here. Call the derivative little f and the antiderivative capital F. That's very, very common. And switched it up on us and called it G, capital G instead of capital F. The notation will eat you up if you let it. So whenever you're wondering, I'm not sure exactly what this notation's telling me, you need to decide, is this giving me a derivative or is this giving me an antiderivative? Hint, when you see a prime, it's a derivative. When you see a capital, it's an antiderivative. Now, is that you can see both, and they don't have to. You can make it any way you want, okay? But the standard way of doing things, capital letters represent antiderivatives. When you see a prime, it's a derivative, which means lowercase letters can be either one. A lowercase f of x can mean the derivative of capital F, or it can mean the antiderivative of f prime. All right? A lowercase f of x can mean the derivative of capital F, or it can mean the antiderivative of f prime. Or it can mean both. Okay? It can mean both. So the regular f that we've been used to is kind of in between. Okay? See? All right, so different notations. When solving the equation of the form dy dx equals f of x, even that's confusing. Derivative on the left, an expression with x's on the right. It is convenient equivalent differential form. You ever seen that before? But before it had an f prime. Yeah, because f prime represented derivative, but lowercase f can represent derivative. Yeah, it's annoying. I'm glad y'all figured that out. I've been saying that for years. It's annoying. Okay? So it is. It's the same idea. The operation of finding all solutions of this equation is called antidifferentiation, or finding the antiderivative. Indefinite finding an integral. And by the way, if there's an indefinite integral, there's a definite integral. We'll get there someday. So, finding the antiderivative can be called antidifferentiation, It can be called indefinite integration. It can be called finding the antiderivative. It can be called finding the indefinite integral. They all mean the exact same thing. And they all also mean the general solution of a differential equation.
Why so many names?
Once we start working problems, one name is more convenient than another sometimes. All right. So the general solution is denoted this way. This means that's called an integral sign. It means find the antiderivative. No, I said the, didn't I? Find an antiderivative. Okay? Now, we've got, so y equals, so our function equals the integral of f of x dx. The way this notation works, capital F is the antiderivative of little f, isn't it? Plus c. So, kind of like we do this, if I wanted you to take the derivative of that, but I didn't really want to name that y or f of x, I could say, find the derivative of that, and you know that that d over dx meant find the derivative of that. If I want you to find the antiderivative of it, I can just put an integral sign in front of it. That means find the antiderivative of it. Okay? Don't worry about it. But the rest of this notation matters too. Okay? That has got to be there. Without the dx, that means nothing. That integral sign in front of an x squared means nothing. Now it means find the antiderivative of x squared. I can explain this better in a few sections, okay? But for right now, think of it this way. If we've got dy dx equals, and I'll just go ahead and say x squared, okay? And this is kind of an algebra trick more than reality. Multiply both sides by dx. I get dy equals x squared times dx. Now, we can do pretty much anything we want to an equation as long as we do it to both sides. I take the antiderivative of both sides. Now, whenever you don't see a coefficient of something, what's the coefficient of something? So there's a 1 there. All right? We're going to learn that the dy means derivative of y. We're going to learn that the antiderivative, well, I can just do it this way. We can say the antiderivative of 1 with respect to y. Well, the antiderivative of 1 is going to be y with respect to y. So that's why that notation means antiderivative. Because what did we do to both sides? Took the antiderivative. Now, I'm kind of getting ahead of myself, and I'm kind of not. It's kind of a big pool of stuff. It's not really learn this, then this, then this. It's learn all this. Yeah. All right, let's see. All right, the term indefinite integral is a synonym for antiderivative. If I remember synonym correctly, it means exact same thing as. All right? All right, so the expression, and I'll say this both ways. The integral of f of x dx is read as the antiderivative of f with respect to x. Think of that for now as being with respect to x. So the differential dx serves to identify x as the variable of integration. For now, x is your variable of integration. Okay? All right. The inverse nature of integration and differentiation can be verified by substituting capital F prime, oh great. We just learned capital F today, and now they're already taking a prime. Capital F prime means the derivative of capital F. Where did capital F come from? It was the antiderivative of little f. The derivative of the antiderivative, which is the original function. Right? Take something, then its derivative, you got to be back where you started, don't you? Okay? So capital F prime of x means the derivative of the antiderivative of little f. This way. Right here. That means take the antiderivative of the derivative of the antiderivative. Now I've confused myself. Think of it this way. See that? That means antiderivative. See that? That means derivative. They undo each other, leaving you with whatever notation they use, whether it's a capital F, a little f, G, a Q, an R, whatever. Like this, right? An exponent of 2 do? Yeah. They undo each other. You get left with whatever's under there. So the antiderivative sign, the integral sign, and the derivative sign, the prime, they undo each other because inverse operations. So we can say cancel. I prefer saying undo each other because you got to realize there's a process. It's not just like off or what, you know what I'm saying? I understand what you mean when you say cancel. You're thinking of the right thing. I get that. Probably sounds, I don't know, undo each other sounds kind of silly in a way, sounds immature, but there's a process. And those two, once you do one process, then the other process, you're back where you started. Yes, they could have said the integral of lowercase f prime of x dx equals lowercase f of x. Now, plus c, because the last thing we did was the antiderivative, and there's always a family of antiderivatives. Now, look at it this way. Believe it or not, you work right to left. You do the derivative first, then the antiderivative. With this notation, you do what first? The antiderivative, which would give us a plus c, then the derivative of that. And what's the derivative of that plus c? So all we have is the f. So it matters. It's not really right to left as much as it is inside out. And you're used to inside out in math, aren't you? So think of that as having a parenthesis around it. You do that first, then you take the antiderivative. Think of this as having a parenthesis around it. You do that first, then you take the derivative. So when you take the antiderivative last, you get a family of antiderivatives. When you take the derivative last, the derivative of that constant is 0. We don't normally write plus 0, do we? Okay, y'all hanging in there? Integration is the inverse operation of differentiation. Differentiation is the inverse operation of integration. Integration rules are the derivative rules in reverse with opposite operations. Now, it's really a lot more difficult than that. Okay? The integration rules we're going to learn are tougher than the derivative rules we learned. Now, let's start at the beginning. The first derivative rule we learned was the power rule. So now we're going to learn the power rule for integration, the power rule for antiderivatives. Write this down. I know it's in your book. Write it down. The integral of x to some exponent n, dx, because for now, just the notation dx has got to be there. I can explain it better later. Equals 1 over n plus 1 times x to the n plus 1 plus c. Now, there is an exception. N cannot equal 1. No. I left off the negative. Negative 1. Do you see why n cannot equal negative 1? Because 1 over n plus 1 would not be anything. Okay? Now, let's go back to finding derivatives for a minute, okay? If I wanted to find the derivative of that, wouldn't I multiply the 3 times the coefficient of 1, then have the x, and then subtract 1 from that exponent? Anti-differentiation is anti in every way. Different order and opposite operations. So the last thing I did was subtract 1 from the exponent. So when you're doing antiderivatives, the first thing you do is add 1 to the exponent. The very first thing I did was multiply the original exponent times the coefficient. So the very last thing I do is divide the coefficient by the new exponent. Opposite order, opposite operation. And never forget, plus c. I have in the past given a quiz with about 20 antiderivative problems on it, and I had to go through the paper doing this. Because they left off plus c. And I will do that to you, and I have to. Because if you go to college and you don't put plus c's, they are not going to be happy with you. Because that's the basics of antiderivatives. Okay? They will not, all of a sudden, your stock kind of went up during the semester doing derivatives. You're going to get there, never put on a plus c, and they're going to think, okay, I was wrong about this kid. I thought they had a future. All right? Okay, that's a slight exaggeration. Slight. All right. So here are your basic integration rules. Derivative rules on the left, integration rules on the right. Now, I'm not going to sit here and read these to you. I want you to go through these on your own time like this. Compare them. Just put a piece of paper there and line them up. Compare, 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 all the way down the line so that you see how it works. Ooh, look at that one right there. Isn't that cool? The derivative of secant x is secant x tangent x. We actually know what the derivative or what the antiderivative of secant x tangent x dx is. It's the secant of x plus c. Yes, they are. Now, with derivatives, quite often we had to rewrite the problem to make finding the derivative easier, didn't we? Sometimes we'd multiply things out or whatever. It's the same thing here. So look on page 251, example 3 on the bottom half of that page. So if you see like part A there, the integral of 1 over x cubed dx, there is no quotient rule for antiderivatives. There never will be a quotient rule for antiderivatives. But you don't need it because you just rewrite your integrand. The function that you're integrating is called the integrand. Rewrite the integrand. Now you can use the power rule on it. So you add 1 to the exponent. And be careful when your exponent's negative. Adding 1 actually goes up. Okay? So you add 1 to the exponent, and then you divide your coefficient by the new exponent. So a coefficient of 1 divided by the new exponent of -2, and I wouldn't have written it that way. I would have written it that way. Okay? I don't recommend doing it that way. Not yet. And then you simplify. You don't like to leave negative exponents in your answer, so you simplify. We know how to find the antiderivative of that. Because isn't a square root really an exponent? So rewrite it in exponential notation. Use your power rule. Add 1 to the exponent. Divide your coefficient by the new exponent. So add 1 to the exponent, right? 1/2 plus 1 is 3/2. Now divide your coefficient by the new exponent. Now dividing by 3/2 is awkward. How do you really divide by fractions? Multiply by the reciprocal. So dividing by 3/2 is multiplying by 2/3 plus C. See how it works? All right. You're just going to have to memorize those. You should have them already almost memorized, right? Because you have the derivative formulas memorized. Memorize the integral formula. Look at these from page 255. Rewrite things. Notice something we can do here. Look what they do in the very first one. That constant factor, not a constant term, a constant factor, they just set it in front of that integral sign. In a few sections, I'll be able to explain to you why. But for now, just know that you can. Okay? Here, you can only take out the 2. You can only factor out a constant. You can't factor out anything else. It's got to be a constant factor. Yep. All right, this one, just like we did before we did the chain, before we did the chain rule for derivatives, wouldn't we have multiplied that out? Multiply it out. Then look what you're able to do. They take the antiderivative of each term. Doesn't that seem reasonable? Since we could take the derivative 1 term at a time, shouldn't we be able to take the antiderivative 1 term at a time? So they added 1 to the exponent, divided by the new exponent. Add 1 to the exponent, divide by the new exponent. That's interesting. The antiderivative of 1 is t. Think about it. What's the derivative of t? So what's the antiderivative of 1? Plus c. Okay? Before we knew the quotient rule, wouldn't we have divided each term in the top by x squared? That's what you do. Then take the antiderivative of each term. Before we knew the product rule, wouldn't we distribute the cube root of x? That's what you do. And change it to exponential notation. Take the antiderivative of each term. Remember how the power rule works. Add 1 to the exponent, then divide the coefficient by the new exponent, plus c. Okay? So, I strongly recommend that you go back and spend some time on these examples and looking at how they've done these. I wish they'd have gone down the page because that's the way we're used to seeing things. Maybe rewrite them down the page. Maybe that'll make more sense to you. Because look, I cannot work enough examples of these for you. I can't. There's not enough hours in the day. So you're going to have to look at the examples in the book. You're going to have to. Because with repetition, this gets easier. It's going to seem really awkward for a while. But with repetition, it gets easier. It really does. All right. The process of finding an antiderivative is the same as finding an indefinite integral, is the same as finding a general solution of a differential equation. Now, we talked about that a few slides ago, right? I think if you write this down, it will help you when we run into actual examples. So I'm going to pause for a minute, let you write that down, and we'll see how it goes. Yeah. Let's begin with number 3 on page 255. It says to verify the statement by showing that the derivative of the right side equals the integrand of the left side. All right, what I want us to do is do what we're familiar with at this point. We know how to find the derivative of the right side, don't we? So let's do that. So let's find the derivative of 1/3 x cubed minus 4x plus c. Now, don't think about what you just learned. Think about old school stuff. What's the derivative of 1/3 x cubed? It's hard to go back to it, isn't it? It's x squared. Exponent times coefficient. 3 times 1/3 is 1. Subtract 1 from the exponent. And the derivative of negative 4x, negative 4. And the derivative of c, 0. Can you factor x squared minus 4? Does that look like the integrand on the left? So they're just trying to convince you that this process gives you the same answer. Okay? They're just trying to show you that taking the derivative of the antiderivative gives you the integrand back. Because, look, that's the that's an antiderivative, right? What do we do to it? Took its derivative. What do we end up with? The original function. Because the integrand is our, think of that as our f of x. That's our capital F plus c. We took the derivative of that, ended up with that. Number 8, find the general solution of the differential equation. All right, so dy dx equals 2x to the negative 3. Multiply both sides by dx to get dy equals 2x to the negative 3 dx. Integrate both sides. Don't actually do any work. Just put an integral sign in front of them both. You can do that on the same line of paper if you want to. I don't care. Now, the integral of dy means the antiderivative of 1 with respect to y. So on the left, y is our variable. So the antiderivative of 1 with respect to y is y, because what, variable not derivative of 1. Okay? So we get y on the left, and on the right, the antiderivative of 2x to the negative 3. Add 1 to the exponent, so the new exponent's negative 2. Divide your coefficient by the new exponent. So 2 divided by negative 2 is negative 1, plus c. Are we fans of leaving negative exponents in our answer? No, we are not. When you do the process of finding the antiderivative, the integral sign and the dx go away. Then they want us to check the result by differentiation. All right. So that's what we say the antiderivative is. So if we take its derivative, hadn't we better get 2x to the negative 3 again? And we do. And the only reason I went across the page instead of down is because I was out of room. Actually, no y there. So the derivative of negative 1 over x squared plus c means the derivative of negative x to the negative 2 plus c, which means 2x to the negative 3. Number 11. All right, we're going to have to rewrite this thing. They want us to complete the table. Now, I need to do a couple things here. One, I don't want to deal with a square root, with a radical. So change x times the square root of x. Think of it as x times x to the 1/2, and x times x to the 1/2 is x to the 3/2. But that's in the denominator. We don't have a quotient rule. Never will. So change that to the integral of x to the negative 3/2 dx. And now we can use the power rule for antiderivatives, or the power rule for indefinite integration. So the integral sign is going to go away, the dx is going to go away. Add 1 to the exponent. So what's negative 3/2 plus 1? Negative 1/2. Divide the coefficient by the new exponent. So divide the coefficient of 1 by the new exponent of negative 1/2. Dividing by a fraction is a lot easier if you just multiply by the reciprocal. So instead of dividing by negative 1/2, I'm actually multiplying by negative 2. Well, 1 times negative 2 is negative 2, plus c. We don't really want to leave a negative exponent in our answer. And since we started with radical notation, we might as well end with radical notation. Number 13. All right, what are we going to do with that exponent of 3 in the denominator? Yeah. The top as well? No. It stays there. So that's the integral of 1/2 x to the negative 3 dx. You can. It's going to work out the same way. Add 1 to the... Now we're ready to integrate. We're find the antiderivative. Add 1 to the exponent. What's our new exponent? Negative 2. And then divide the coefficient by that new negative 2. And in this case, since our coefficient's a fraction, Dividing by negative 2 is easier to think of it as multiplying by negative 1/2. Right? So what's 1/2 times negative 1/2? And that's an antiderivative. Do we like the negative exponent in our answer? Uh-huh. So I took 1 and divided by 2. It's easier to think of that, well, it's easier to think of that as 1/2 times negative 1/2. How are we doing? Number 28. All right, we got to divide each term in the top by x to the 4th. What's x squared divided by x to the 4th? Yeah, it's an x squared in the bottom, but we'd rather write it as x to the negative 2, hadn't we? So we can find the antiderivative. Yeah, when you divide factors with the same base, you subtract the exponent. So then 2x divided by x to the 4th is 2x to the negative 3, and negative 3 divided by x to the 4th is negative 3x to the negative 4. See if that's what you get for the next step. And on this one, I'm not going to bother putting all that back into one fraction. That's just a bit much.